Hello all, welcome to my course on methods of adhesion measurement theory and practice. Today we are at lecture 27 and we are discussing about adhesion experiments using cylinders. Before I start today's topic, I thought I would give you today the list of different references that I have so far cited about or taken from my lecture notes. So, from lecture 1 to 4 I took it from this particular book and some general reading from different elasticity books. Lecture 5 to 16 I took the topics from contact mechanics from first 2 chapters, and then lecture 17 to 20 this was from this paper by Van Os at Chemical Reviews, and then this particular paper by Professor M. K. Chaudhary, Manoj Chaudhary, interfacial interaction between low energy surfaces. Then lecture 22 to 24 I took it from this particular paper by Professor K. L. Johnson. So, this is on JKR contact mechanics, surface energy and contact of elastic solids. Then this another paper by Professor Chaudhary's group, Katharina Varvalakas et al., Langmuir 2003 paper. And then 25-26 I took it from this particular paper by Professor Chaudhary, Journal of Applied Physics 1996. Today we are at lecture 27 and today we will talk some of the things from this particular paper by again Dr. Chaudhary's group on estimation of adhesion hysteresis at polymer oxide interfaces, in a sense some hysteresis aspect that I will talk about today. So, we are talking about these 2 cylinders with their axes parallel to each other in contact, and we have derived this expression of pressure at the interface. So, in essence what we have is basically this particular cylinder, let us say, and this cylinder is in contact with either with another cylinder like this, or let us say it is in contact with a flat plane, that is also possible, and then the contact area is A, let us say, and so what is the pressure distribution at considering this is symmetric at A at within this contact area, that is what is the distribution here. Now, in absence of adhesion we can simplify this equation, the pressure distribution in this form. So, that at x is equal to A, so that means at the edge of this contact area contact width, the pressure becomes equal to 0, basically atmospheric. So, it is 0 here, and for the total pressure can be obtained by this equation by simply integrating this p x over d x from minus a to a, one can actually get this expression. So, we have derived this equation in the last lecture. So, today we will like to talk about adhesion, that what happens when there is adhesion between these 2 cylinders, or let us say that one cylinder and one flat plate, and let us say the cylinder is deformable, and then we will see that we can borrow some ideas from fracture mechanics to derive the work of adhesion, that is what it is. So, here for example, that this is the pressure distribution between let us say there is a flat plate and let us say that there is this cylinder in contact, and now the pressure it is some load is applied over here. Now, there is adhesion between them. So, if I magnify this part, so it will look something like this. So, there is some amount of stretching that will happen of this particular cylinder. So, the contact radius, let us say this is up to a 0, now it will become a 1, I have already discussed in regard to the spherical geometry. And so, what happens is that in this portion it is looking like a crack. This is a crack in mode 1. So, mode 1 crack is something like this. So, let us say we have got a body. So, we apply some load here or some torque here and we try to open it. So, the crack propagates in this direction. So, this is called mode 1 crack, right, and then of course, there are mode 2 crack. So, mode 2 crack is something like this. So, let us say we have got one body here, another body here, kind of lap joint, and let us say we apply the load. So, there are fracture occurs at the interface, that is called crack mode 2, and then there is a mode 3, that is out of plane bending. So, now this we have what we have here is kind of mode 1. So, in the mode 1 case, so in regard to here there is a pressure applied here. So, it is compressive in this zone at the middle and it becomes tensile outside. So, close to the crack tip the stresses become tensile, and at the towards the middle the stress becomes compressive, that is the way it happens. So, the fracture occurs because of this tensile tensile load that happens at the towards the edge of this contact area, or if you say fracture mechanics. So, this is a crack tip. So, this what happens here, basically the stress concentration that happens because the stresses become singular at the crack tip, and as a result of this singular crack, so crack propagates. So, therefore, since this particular edge contact edge over here in the context of adhesion looks like a crack tip and there are stress concentration happens. So, we can actually borrow the ideas from the fracture mechanics. So, that is basically the idea here. So, now what is the kind of stress concentration that happens, that we can get from this and from this equation. For example, here I can write this P x as 1 upon pi and square root of a minus x into a plus x, and x is what, from the center towards the outer edge. So, x is distance, x is less than equal to a, and then here I have p minus this pi e star by 2 r into x square minus a square by 2, like that. So, now what is the kind of stress that will happen at the edge? So, that I can write it as, let us say I write it sigma z, and let us say write it at x, and at x tends to a, close to a, what happens. So, stress will be negative of pressure. So, it is minus sign here on 1 here, and this is pi here, and then I call it not equal sign, let us say I say it almost equal to, it is here. So, it is a minus x here, and since x tends to a, so I put here x is equal to a. So, I get here 2 a, and here this is p and minus this is pi e star by 2 r, and again x is equal to a. So, it is a square minus a square by 2, like that. This is because I am actually using at x tends to a. So, at close to at the edge of the contact width, what is the stress, that is what I am trying to find out. So, pressure is, this is the equation. So, the negative of that is stress, and so that therefore, sigma j, that is the normal stress, will be here like this. And if you see this equation, I can write it as, express is that something like this, k I will say in a minute what is this k I, let me write it properly. This is, let us say k I, and this is let us say square root of 2 pi and let us say a minus x. So, in a sense, if you see what is this a minus x. So, a from the center to a is this point, right. So, this is let us say a over here, and a minus x is somewhere here. So, x is here. So, a minus x is this region, a minus x. So, it is in this region where the crack propagates, where the stresses remains concentrated, that is what we are saying, right. So, this a minus x in this is this region here, and it is here the stress remains concentrated, the tensile stress. So, it is very close to the crack tip. So, this is the region, the distance from this crack tip, that is defined by this quantity a minus x, and this capital K 1 that I have written, this is called the stress intensity factor in mode 1 crack propagation. This is called stress intensity factor in mode 1 crack propagation. So, that is what it is. So, of course, the if we can just simply relate this k I to these quantities. So, over here let us say this is the relation that we have gotten here, and yeah. So, over here so this is, as I wrote, this is k I by square root of 2 pi and a minus x, right. And so, therefore, what will be k I? So, K I will be here, this is square root of pi. So, there should be a square root of pi here. So, square root of pi here, and this is a minus x, it is square root of 2 here. So, let us say square root of, so this is pi a here, the square root of 2 goes, okay, and then it is p minus pi e star a square by 4 r. So, here like that. So, this is the expression for this stress intensity factor. So, this is one idea that we have borrowed from fracture mechanics. Now, why did we do this? Because in fracture mechanics there is a way to calculate the strain energy release rate. So, what happens when this crack propagates, the energy that is stored because of the tensile load, that gets released, okay. And in fracture mechanicians they have developed a way to calculate that energy that gets released. So, they call it G, and let us say G here, yeah, G. So, that is called the strain energy release rate. So, it is called strain energy release rate. So, fracture mechanicians they have developed, and they say that G will be equal to K I square by 2 E star, like that. So, here I can therefore write it to be 1 by 2 E star here, and K I square will be 1 by pi into A, and this is P minus pi E star by A square by 4 r whole square. Now, this is the strain energy release rate. So, that means this is the amount of energy that gets released when the crack propagates, right. And in our case, when the crack propagates, there are two new surfaces that forms. So, the crack comes over here. So, now there is a two new surfaces that created, and we know that from an interface when the two surfaces get created, that is basically the energy of adhesion, work of adhesion. Now, for brittle fracture, when there is no viscoelastic or plastic or any other losses, then this G can be equated to, okay, work of adhesion. For brittle fracture, that can be done, because that whatever is the strain energy that was stored in the material, that has got released because of this fracture, because of this crack propagation. So, this is brittle fracture, okay, we can actually use this. So, see, we have a very nice way and simple way to estimate this work of adhesion over here, okay, by using this idea from fracture mechanics. So, here therefore, this G, okay, is the so as I said that work of adhesion W, okay, will be equal to G. So, this G W now can be expressed as this work of adhesion here W A, that can be expressed like that. So, we can further write that use E star is equal to 3 K by 4, and then we substitute over here. So, we can just get this particular expression, we can rearrange this expression, and we know that in experiments we get the data, okay, in terms of P A as a function of P. So, we can actually rearrange this data also. So, now work of adhesion is obtained like that, and let us say that what we get P here. So, we can write P is equal to, therefore, it will be 3 K and W by 2, 3 K W is the work of adhesion, let us say A I write here, W into pi into A square root. So, it is I should be minus here, minus, and then plus here, it will be 3 pi this is K, 3 pi, this is K A square by 16 r. So, 3 pi K W A, okay, 3 K by 2 into W A into pi I square root, okay, and plus here, right there, that is okay. So, now this is, remember that so this was the cylinder, let us say that this was in contact with another cylinder or a flat plate, and this was the contact to it. So, if I see from the top, I will see something like this, the contact to it to look like that, and let us say that this, the length of the cylinder is 2 L. So, it is like this, and this quantity is actually 2a, like that. So, what I do is multiply this. So, P is the line load or the line load per unit width. So, that is per unit length over here. So, we multiply P by 2L. So, I will have here therefore, F, and that will be equal to 3 pi k a square 16 r into 2L, okay, minus it will be square root 3 k by 2. So, it is 6 here. This is because L square. So, 6 k L square W a pi a W a pi a. So, I do not have anything else. So, let me write in without ratio here. So, it will be 6 k L square W a pi into a, like this. So, this becomes, so here 2 and 16 you get, you can cancel it, we get here I 8 here, like that. So, we in the experiment, okay, I will measure basically F and we will measure A here, and then we can arrange this equation to obtain the work of adhesion and the elastic modulus, this quantity K here. Remember that we did it for the JKR contact mechanics, okay, using we have done it for JKR contact mechanics, and where we did the same thing. So, now let us say that the now what it means, let us see. So, how does this F will vary with respect to A? So, from a typical experiment, this, so we vary the load F and we measure A. So, here this is the loading part of this particular data, okay, and this is the unloading part. So, this is the unloading part. So, normally this is the way we will see. So, this is the work of adhesion, right, and during the loading part, let us say we start from some finite value of the contact area. So, at which time the load will be estimated to be found out to be this, and then the load increases as we load is increased. So, the load increases and then along with that the contact area also increases, let us say. Then we decrease the load, and what it so happens that the load here does not follow exactly the path, the loading data, the unloading data do not they do not follow the loading data curve. It comes down like this, and then it decreases, the load becomes negative over here, and then finally at some point of time, some width, contact width, it goes to 0. So, basically what we say is that we get a minimum, okay, load. So, basically this negative means this is the pulling load. So, here this capital F, that means this is the compressive load. So, as you compress it more, the contact width increases, but the negative side it is a negative, means a pulling load. So, the contact width decreases, but at a negative load, because of the adhesion, contact width does not go to 0, just like that, it actually decreases, goes to some minimum. So, as the contact width further decreases, the load again increases, and there is some kind of instability that we see. We are not very much concerned about that instability part over for this part of the course, and so we see the minimum. So, there is a minimum load that is there. So, that minimum load can be found out by writing del F by del A equal to 0, and that will be equal to here, for example, 3 pi k L 2 A by 8 r, and minus this is square root of 6 k pi W A L square, and then this is square root of half. So, it is square root by 1 by A, and this is equal to 0. So, then A cube, we will get an expression for A cube here. So, A cube will be equal to this is 4 here, okay, let us see, 8 r by 3 pi k L, and this is 2 into 2 4 into 4 here, right, 4 into so 2 goes over here. So, I have taken 2 here. So, it is 6 k pi W A L square, like this. So, 4 and here it is 2 here. So, it can be taken inside here. So, here let us say it will be equal to, it is 4 by 9 here. So, 4 by 9 here, this is r square there, this is here pi square capital K square L square, and here 6 k pi w a L square. So, this L square is cancelled, this k and the k gets cancelled, this pi and this pi is over here, and this is 3. So, it is 2, it is 3 here. So, it is square root of 8 by 3. So, doing all that, okay, we can get a minimum value here. So, here we get a value for A as this. So, after doing all that I did, so the contact width and this is basically we say the contact width at the separation, or that means the minimum load that can be applied, or that is the maximum tensile load at which the separation happens. So, this A can be substituted into the expression for F to find out what was that F min. So, that gives us the pulling load that needs to be applied. So, that load can be written here. So, let us say 3 pi capital K L and 8 r. So, A square is 8 w r square by 3 pi k, and this is A to the power 2 by 3 square is there. So, 8 pi w r square 3 by 2 by 3 minus this is square root, and here 6 k pi, this is w and L square w square into A. So, again it is A to the power 1 by 2. So, let us take it outside, A to the power 1 by 2. So, I will write over here, it is 8 w r square by 3 pi k, and this is 1 by 2, it is 1 by 6 here, okay, like that. So, here once again all these arrangements have to be done, rearrangement has to be done, and finally, one can do little bit more algebra. So, one can get here like this F min. So, I did all that, and finally, one will get here something like this L w square blah blah. Now, it are coming out to be 81 pi by 8, and this particular term, okay, once you take it out you get it something like this. So, basically this is F min, it comes out to be minus 3.168 L into w square r capital K whole to the power 1 by 3. So, this is basically the pull of load, pull of force that is required to separate the two cylinders in adhesive contact with their axes parallel to each other, or let us say cylinder and a flat plate. So, that is all, that is the way it comes out to be. And if you want to, and then let us say a small problem we take. So, an elastic cylinder, okay, Young's modulus E1 2.8 megapascal, radius 5 millimeter is brought into contact with a flat elastic half space that is 0.5 megapascal under a load 25 millinewton. The Poisson ratio cylinder and the half spaces are given, and the work of adhesion between the two material is 50 millijoule per meter square, obtain the pull of load. So, in essence what you have to do, we have to use this particular equation here, and here we have to estimate this r and k, capital K here, L is already given let us say, and so this k means this is Young's modulus, effective Young's modulus that needs to be calculated, r means relative radius of curvature that needs to be calculated. So, let us do that. So, it is let us say 1 by E. So, that is given as 1 minus sigma 1 square by E1 plus 1 minus sigma 2 square by E2, and that is equal to 1 minus 0.48 square by E1 is 2.8 into 10 to the power 6 Newton per meter square, plus this is 1 minus 0.49 square divided by this is 0.5 into 10 to the power 6. So, this is Newton per meter square inverse, and then we find out K as this is actually E star. So, we find out as 4 E star by 3. So, whatever we get we have to multiply that quantity over here. So, whatever we get we have to use the calculator like that, and then r will be 1 by r, relative radius of curvature will be 1 by r1 plus 1 by r 2. So, 1 by r1 is here 5 millimeter, 5 into 10 to the power minus 3 MKS unit is one that we are using, and this is a flat plate brought into contact with a flat elastic half space. So, R2 is equal to infinity. So, this is equal to 0 here. So, here this many meter inverse. So, I can get R is equal to 5 into 10 to the power minus 3 meter. So, we have all these quantities now, and we have work of addition as well. So, we can use this relation F mean is equal to minus 3.16, and remember what is the length of this cylinder, okay, per unit length. So, remember the length is 2L, right, it is 2L. So, we have to be careful about that, and so actually we have to divide it by 2L. So, F mean by 2L. So, it will be divided by 2 into this is W r square into K. So, W is already we have, that is 50 millijoule per meter square. So, 50 into 10 to the power minus 3 W square r into K. So, into r, that is 5 into 10 to the power minus 3 into K. Let me just see what value of K I got here, 0.743 10 to the power 6, 0.743 into 10 to the power 6 here. This is 1 to the power 3. So, here you have to divide it by 2. So, here I did little wrong here. So, it has to be divided by 2 here to obtain 3.33. Okay. So, do not make this mistake, because the length was actually 2L. Okay. So, here I have to divide it by 2 here, I should do it here. Rest of the things are fine. So, I have done it, taken care of it. So, the pull of load will be given by this expression. So, I think I will stop here today, and I will take up some more concept about this cylinders in contact. I will like to take up the hysteresis of in the cylindrical contact with the cylinders in the next lecture. Thank you for your kind attention.